Welcome back to Differential Calculus. In this video, I want to take a bit of an aside from the normal flow of the course to talk about summation notation. It's possible, depending on what path you have taken to get to this course, that you've come across the basic ideas of summation notation before. And I'll be honest, I'm not going to go any further than the basic ideas of summation notation here. But my expectation is that you haven't seen this before, so I'm going to treat it as some new ideas. Let me get my head out of the way, and we will start off with a sequence. A sequence we generally write using subscripts, so A sub k is a sequence. And very often, for reasons that I don't really want to get into today, you're going to see a sequence written with curly braces around it. And that subscript k is pulling a lot of weight here, because the basic idea of a sequence is that if you put in a particular value for k, you will get a different result out. A1, A2, A3. Things repeat. Wait a second, though. You put in a value for k, you get something out. That's the definition of a function. It's just a little bit of a strange function, because you have to put in a natural number, a positive integer, in order to get something out. You cannot use any real number. And that's why we use the subscript notation. Technically speaking, there is no reason we couldn't write a sequence A of k, but we don't in order to emphasize that we need to evaluate these things on integer values, not on real number values. And with the idea of a sequence in our back pocket, we can go to the next idea, which is a summation. And the symbol for a summation is this guy here. This is the Greek letter capital sigma. A lot of people look at this and think of it as being some sort of, as an M, that we are going to read this thing as the sum. And I didn't quite give myself enough space, so let's get that a little bit further out of the way so that I can continue. Below the summation symbol, we're going to write a starting point. For our purposes in this course, it is always going to start with k equals 1, and it is always going to end with some integer capital N. And in any given problem, everything is going to stay the same for us in this course. For those of you who are moving onward, one of the things that I do want to point out is that in Calc 2, in discrete math, in differential equations, you will come back and revisit the idea of summations. And when you do, the starting point may change. It might not start at k equals 1. Sometimes it will start at k equals 0 or k equals 2. Or if you go far enough, you actually get to k equals negative infinity, which really starts to mess with you. And the end point, n, does not have to be the same. It doesn't have to be consistent. We're going to be consistent in this course this semester. And I'm going to tell you from experience, that is going to make many of you want to develop a bad habit of leaving these things off. And if you do that, and then continue onward, you are going to be very confused when you look back at your notes and you realize you left all of the indices off of your summations, and everything is off what you're trying to be doing. So, I speak from experience when I tell you, get in the habit. Put your starting point and your ending point on every summation, because it will mess with you later if you try to stop and shortcut it now. All right, but we have the sum, k goes from 1 to n, of our sequence, ak. And by definition, we're just going to add together a1, a2, and keep going until we get to an. And practically speaking, this is usually not that difficult to follow. It seems a lot crazier in the example or in the definition than it does in an example. Let's draw that summation symbol a little bit bigger. All right, the sum, k goes from 1 to 5 of 2k minus 1. All right, well, we plug in k equals 1. 2 times 1 minus 1 is 1. We plug in k equals 2. 2 times 2 minus 1 is 3. Plug in k equals 3, we get 5. Plug in k equals 4, we get 7. Plug in 5, and we get 9. That's it. That's all there is to it. I say that, and as soon as I say that, people start to get concerned. Because, no, that's not all there is to it. That's the definition, that's how summations work, and when you have a relatively small index, like bigger. The sum, k goes from 1 to 100 of k. Add up the first 100 numbers. And we'll be here for a while. Even if you take the time to plug that into a calculator one by one, it takes a while to get everything going. Here's where I said you may have come across this in the past because there is a shortcut formula. As the story goes, one of the greatest mathematicians of all time, Carl Friedrich Gauss, was assigned this problem by his 5th grade equivalence teacher. And the teacher just wanted to keep all the students busy for a while. And Gauss looked at the problem and realized that, well, you can take a shortcut. Instead of trying to add everything up, notice that if you add 1 and 100, you get 101. If you add 2 and 99, you get 101. 3 and 98 gives you 101. 101, 101, 101. Well, how many times do you have to do that? Well, you do that once for every 2 of the values here. And so he realized that there was a nice special case formula. The sum, k goes from 1 to n of k, is n times n plus 1 all over 2, no matter what value of n you choose. And that is how we're going to deal with this. We're not going to add 1 plus 2 plus 3 and keep going. We're going to plug in n equals 100. And we're going to see that this is 100 times 100 plus 1, which is 101, all divided by 2. 100 divided by 2 is 50. 50 times 101 is 5,050. And this is the first of the formulas that I have to work with here. A couple of others. Again, anyone who's continuing onward to a course in discrete mathematics, you'll see a little bit more of how we figured these things out in that course. If you continue onward from there to something like number theory, you'll see a lot more of it. But the sum k goes from 1 to n of k squared is n times n plus 1 times 2n plus 1 all over 6. And the sum k goes from 1 to n of k cubed is n squared, n plus 1 squared, all over 4. A couple of other formulas that are worth knowing. This one is very simple. K goes from 1 to n of some constant c. This expression tells you to add c to itself n times. Add something to itself a whole bunch of times is the definition of multiplication. So you get c times n. And the last one is probably the most important. The last one is linearity. If we have the sum, k goes from 1 to n of some constant p times ak plus some other constant q times the sequence bk, you can distribute the summation throughout the constants. P times the sum, k goes from 1 to n of ak plus q times the sum, k goes from 1 to n of bk. There's not a lot of things where we can distribute. There's not a lot of things that have this nice property of linearity. So when you have them, you celebrate. That is going to make this process go from very difficult to very straightforward. To see what I mean, let's get all of those rules off the page and take a look at another example. The sum, k goes from 1 to 25 of k squared plus 3k minus 7. Using the rule of linearity, I can split this summation up. The sum, k goes from 1 to 25 of k squared, plus 3 times the sum, k goes from 1 to 25 of k minus the sum, k goes from 1 to 25 of 7. Then, using our summation rules, the sum of k squared is n, 25, times n plus 1, 26, times 2n plus 1. 2 times 25 is 50, plus 1 is 51, all divided by 6. The sum on k is n, 25, times n plus 1, 26, all over 2. And the sum on 7 is 7 times n, which is still 25. My calculator is happy to work through this arithmetic for me. 25 times 26 times 51 divided by 6 comes out at 5,525. 3 times 25 times 26 divided by 2 comes out at 975. And 7 times 25 comes out at 175. Now, add and subtract 5,525 plus 975 minus 175 comes out at 6,325. All right. One more example. The sum, k goes from 1 to 43 of 2k plus 3, the whole thing squared. What I want you to notice in this particular expression is that this is not linear. The exponent is outside of the addition, and so we cannot use our linearity property to expand this out. But it's just squaring a polynomial. We know how to square a polynomial. 2k squared is 4 times k squared. 2k times 3 is 6k, and we'll have 2 of those, so it'll be 12k. And then 3 squared is 9. Now it is linear. Now we can split it up. 4 times the sum, k goes from 1 to 43 of k squared, plus 12 times the sum, k goes from 1 to 43 of k, plus the sum, k goes from 1 to 43 of 9. And same summation rules we used before. Sum on k squared is n, 43, times n plus 1, 44, times 2n plus 1, which is 87, all over 6. Sum on k is n, 43, n plus 1, 44, all over 2, and sum on 9 is 9 times 43. And once again, grabbing out my calculator, 4 times 43 times 44 times 87 divided by 6 is 109,736. 12 times 43 times 44 divided by 2 is 11,352. 9 times 43 is 387. And if I add those things together, and my calculator doesn't fail me because the 7 button doesn't work anymore, I will get 121,475. All right, that's all there is to it. Let's wrap up with one for you to try on your own. I want you to look at the sum. K goes from 1 to 76 of k cubed minus 3k. All right, take a couple of minutes, see what you can do with that one, and I'll see you in the next video.